Bismillahirrahmanirrahim. Assalamu alaikum, students. Today I'm going to start the lecture series for fifth semester students. So I named this course as, let me write the course name. Course name is fifth, fifth semester physics GDC B1. Government degree college B. Now this course will cover and uncover the syllabus prescribed by the Kashmir University for Jammu and Kashmir colleges, which are affiliated with the University of Kashmir. But these lectures would also be helpful to other colleges outside our state because more or less the syllabus at this level is same throughout our country. Now, you can download the syllabus from the Kashmir University website, or I've also shared the syllabus uh, of the university for this particular semester or in your WhatsApp group also, right? Now, the this semester the course name for this fifth semester is Modern Physics First, and the syllabus is separated into 4 units as usual. So we have unit 1, then we have unit 2, then we have unit 3, then we have unit 4. I will give brief outline of the syllabus, then we will start the course in detail. Now in unit 1, we have discussed the ideas like black body radiation, Planck's radiation law, photoelectric effect, Compton effect, Heisenberg's uncertainty principle, and other related ideas. Unit 2 deals with Schrodinger wave equation, time independent form, expectation values, particle in a box, this tunnel effect, and quantum numbers broadly. And Unit 3 deals with the electron spin, Stern Gerlach experiment, Pauli's exclusion principle, angular momentum, ideas related to angular momentum, Alice coupling, JJ coupling, Zeeman effect, and quantization of rotational energies. Then we have Unit 4, which deals mainly with the particle physics. There we have to discuss ideas like liquid drop model, Meson theory of nuclear forces, nuclear composition, gamma theory of alpha decay, Pauli theory of beta decay, and there is some elementary introduction related to quantum numbers pertaining to particle physics, quantum numbers of particles, right? So we will start with unit first. So today we will discuss the black body radiation. So let us move. So we are starting with unit first. Our first topic is black body radiation. Right here, black body radiation. Now, you must be familiar with this idea The idea is like this. If you take some iron rod, for example, this is my iron rod, right? Now I heat it. As I heat this iron rod, what will happen? Its temperature will increase. Its temperature T will increase with time as I heat it. It will radiate heat as well. If you put your hand closer to this rod, when it has attained some temperature, you can feel the warmth. That means it is radiating heat as well. Now, when it radiates, this phenomenon is actually called thermal radiation. So, all objects radiate electromagnetic energy at any temperature. Now, you know the electromagnetic waves are many. You can have microwaves, you can have X rays, you can have gamma rays, we can have light, that is visible light, we can have infrared. There's, you have gone through the electromagnetic spectrum. You can have UV light. Now, all these waves are electromagnetic waves. There is only one difference fundamentally, the difference between the length of their wave, that's wavelength difference or frequency difference. Now, when you heat this iron rod, its temperature changes. As the temperature changes, its spectrum changes. By spectrum, I mean it is emitting electromagnetic radiation of various frequencies. Now, the amount of energy it is radiating per frequency pertaining to some frequency, that amount of energy will change as temperature changes. But it's not emitting only one kind of wave, it is emitting electromagnetic waves of different frequencies. At some frequency, the energy radiated is maximum, at some other frequency, the energy radiated is small. Now, this phenomenon is called thermal radiation. All objects radiate this electromagnetic energy due to temperature. Now, to understand the phenomenon of thermal radiation, we define an ideal body, that is black body. Now, what is black body? By definition, a black body is the body, let me write it, that absorbs all radiation incident upon it, regardless of frequency. The body that absorbs all radiation incident upon it, regardless of frequency. So, this is the definition of the black body. That means if you shine radiation on black body of various frequencies, it will absorb all of them. It will not discriminate between different frequencies when it comes to absorption. Now, why we introduce this ideal black body in the discussion of thermal radiation is that we can now disregard the precise nature of whatever is radiating because all black bodies behave identically. I repeat, in the thermal radiation discussion, using the idea of black body, we can disregard the precise nature of whatever is radiating because all black bodies behave identically, right? This is the setup of physics. We define ideal things, but ideal things are defined in such a way that that can be used in real situations. You might be knowing that we define ideal gas as a gas which satisfies ideal gas equation PV is equal to nRT, and we know all real gases behave like ideal gas under certain conditions. The condition is when they are kept at low densities, or you can say when they are kept at high temperatures and low pressures. Now, under those conditions, all the rules which we develop for ideal gas can be used for real gases. Similarly, we develop ideas related to black body. It helps us to move forward, develop things, make predictions in case of thermal radiation. Then, when we have to use those ideas for some real body, we see by how much it is closer to being black body that we take into consideration and use the results. Now, how we in practice make this a black body in lab. Now, what we do, we create a cavity, we create a hole leading in the cavity. For example, let me draw this. This is called cavity approximation of a black body. What we do, we create a cavity, and there's a hole in this cavity. This portion is solid. We have produced a cavity in some material. Now see if, let me change the color of the pen. Let me use this color for light. Now if light enters into this cavity through this hole, it will be reflected by the cavity walls. First, it will be reflected at this point, then it will be reflected at this point, then it will be reflected in some other direction. Now, due to these multiple reflections, ultimately it will be absorbed by the cavity. So there is least chance that when we shine radiation at this hole, that it will leave the cavity. It will be certainly absorbed, right? So that makes our definition fulfillment because we define black body as the body that absorbs all radiation incident upon it. So this is how we approximate the black body in the lab. Now the cavity walls are constantly emitting and absorbing. When we heat up this cavity, these cavity walls will be emitting and absorbing constantly radiation, and it is in the properties of this radiation, which we call black body radiation, that we are interested in. Right? Now, this problem, the problem of black body radiation, was examined at the end of the 19th century by two physicists. One is called Lord Rayleigh, and second person is called James Jeans. What they did, they examined the at the end of 19th century the spectrum of this black body, the spectrum of this cavity, approximate cavity radiation. Now, how when we experimentally uh, observe the radiation emitted by this black body or this cavity, then we graph it, we get this pattern. Let me draw this figure first, then we will move forward. I will change the color. Let me use this color. So the graph is like this. On this side, what we plot u of nu d nu. What is that? I will tell you. We call this quantity as spectral energy density. On this side, we plot frequency. As I told you, at any temperature, bodies radiate electromagnetic radiation. Now, when we talk of black body or ideal body, its spectrum, we will graph it first. Now, first, let me clear this quantity. This U of nu, the nu, which is called spectral energy density, it is by definition what? It is the energy per unit volume, which is energy density, radiated by the black body in the frequency interval from nu to nu plus d nu. As I told you, the black body radiate energy at different frequencies, but we are graphing it as energy per unit volume, which is energy density. But energy density in the frequency interval from nu to nu plus d nu. Now, when we plot it, we get like this. I will use this color. The pattern of the graph is like this. This is my zero. Let temperature of the black body for this particular curve be this absolute temperature. Temperature in kelvins, 1200 Kelvin. Now, if you change the temperature, I will use another color for this. Let me use green. The graph goes like this. This is rough. 1800 Kelvin. This is the experimentally observed black body spectra. Spectra is the plural of spectrum. By that I mean there is not energy is not radiated by this black body at a single frequency. It radiates energy at this frequency at different frequencies. As you move towards right, the frequency increases. Now, when the black body is kept at this in first curve, the temperature is 1200 Kelvin. This 1200 Kelvin. And in the second curve, green curve, temperature of the black body is 1800 Kelvin. Now see what changes occur. First, observe the curve. The energy radiated per unit volume in this particular frequency, nu to nu plus d nu, changes with frequency. At this frequency, there is peak. That means at this particular temperature, 1200 Kelvin, the energy radiated is maximum at this particular frequency, at this particular temperature. When you increase the temperature, the peak has shifted. Now, the peak, that means the frequency at which maximum energy is radiated by the black body, goes to higher frequency. At higher temperature, this peak shift is to higher frequency. This is one thing. And second thing, you can see at higher temperature, the area under curve is greater than at lower temperature. This problem, as I told you, was examined by Lord Rayleigh and James Jeans at the end of 19th century. Now, what they wanted to justify this black body spectrum. Justify means they wanted to predict write some formula for this nu news, which can be graphed and which matches these experimental curves. That means they wanted to explain this spectrum using theory, right? Now, what they did, they started by considering the radiation inside a cavity of absolute temperature T, whose walls are perfect reflectors, to be a series of standing waves. I repeat, you must be knowing the idea of standing waves. What is standing wave? If you define it, let me use another color here. If you define it, you can define it as pattern of nodes and antinodes. Pattern of nodes and antinodes. You also know from your previous classes that standing waves can be created in some string. If you have a string, uh, this is string, my string. If this is string, now you can create standing wave in it. Now, how you create? If a wave travels in this string in this direction, and it is another wave is the wave is reflected at the end, and you send another wave in this direction. Now, the traveling waves moving in opposite directions, they interfere and the standing wave is produced. So you say mathematically standing wave is mixture of two traveling waves moving in opposite directions. Now, when two traveling waves interfere, which are moving in opposite directions, what happens in the medium? In the medium, the standing wave pattern is produced. What is standing wave pattern? In the medium, there are certain points which are called nodes, which are at rest always. And there are other points in the medium which oscillate at with maximum amplitude. They are called antinodes. Now, the pattern of nodes and antinodes is called as standing wave. Now, the standing wave can be created in one dimension, it can be created in two dimensions, it can be created in three dimensions. Now, Lord Rayleigh and Jeans considered the radiation which was in the cavity as standing waves. They considered them the radiation in the form of standing waves, which was, of course, the three-dimensional form of standing waves, right? Now, when standing waves are created, whether in one dimension or two dimension or three dimension, now there is restriction in them. For example, when in this string, which is kept, which is tied to the two ends in this way, uh, there can be many modes of oscillation, but in all modes, the ends will be nodes. That means the ends will be at rest always. Now, one mode is this. There is another possible mode. There can be many modes. Another possibility is the string can oscillate in this fashion. In this fashion means there can be one node in between also. This is node, this is node, this is node. Here it is antinode, here it is antinode. And the string is oscillating in such a way that these nodes are always at rest, and the this point and this point, the two antinodes, at this point the displacement is from the mean position is maximum. That means amplitude is maximum. Now there can be multiple ways for this string to oscillate. We call them modes of oscillation. Now, because the string is bound at the ends there are always nodes. So the wavelengths possible or the frequencies possible are restricted. There can not be any frequency available, any frequency or any wavelength available in these modes. Only certain frequencies or certain wavelengths are available, or I should say, this string can oscillate only at certain frequencies or certain wavelengths. Right. Similarly, Lord Rayleigh and James Jeans considered the radiation in the cavity in the form of three-dimensional standing waves, and the condition for standing waves in such a cavity is that the path length from wall to wall, whatever the direction, must be half must be a whole number of half wavelengths. I repeat, the condition for standing waves, because this you can see from this point to this point, it is half wavelength. From between two nodes, you must be knowing two consecutive nodes are lambda by 2 distance apart. From this point to this point, it is also lambda by 2, it is lambda by 2. You can understand this string situation from this string situation. Now, in this situation, the distance from this node is half wavelength. In this situation, it's two half wavelengths. And another mode you can construct, there will be three half wavelengths because at the ends there are nodes. Similar is the case of the cavity radiation. If you consider them radiation in the cavity as standing waves in three dimensions, and the cavity walls are considered as perfect reflectors, that means the ends of the cavity walls must be nodes. Therefore, the path length from wall to wall, whatever the direction, must be a whole number of half wavelengths. That means it can be 1 lambda by 2, then it can be 2 lambda by 2, then it can be 3 lambda by 2, and so on, so that a node occurs at each reflecting surface. Now, Rayleigh and Jeans calculated the number of independent standing waves in the frequency interval between nu and nu plus d nu per unit volume. Let me write it. So, Rayleigh and Jeans did what? They calculated the number of independent standing waves in the frequency interval between nu and nu plus d nu per unit volume per unit volume in the cavity. We denote this thing by g of nu d. What is g of nu d nu? It is number of independent standing waves in the frequency interval between nu and nu plus d nu per unit volume in the cavity. Now, when we used this symbol for this, when they calculated, it turned out to be 8 pi nu square d nu by c cube. 8 pi nu square d nu by c cube. I name it first. I repeat what they did. First, they considered the radiation. What was the purpose? Purpose was to explain this black body spectrum. What they did, they considered the radiation in the cavity as a three-dimensional standing wave. Then they calculated this number 8 pi nu square d nu by c cube. Nu is frequency, 8 is pi is constant, c is the speed of light in vacuum, right? You can derive this formula, or we are not deriving this formula for g nu d nu in this lecture because it is not required. You can go through any book, this derivation is available. Now, this formula for g nu d nu is valid for cavity of any shape. That means it is independent of the shape of the cavity. Is independent of the shape of the cavity. That means it is valid for the cavity of any shape. You can see the pattern in this quantity. As nu increases, this quantity increases. So higher nu means shorter wavelength and the greater the number of possible standing waves. Now the next step, because the purpose was to find out the expression for the energy density. Now they calculated the number of standing waves available in unit volume of the cavity. The second step is to find somehow the average energy per standing wave. Then what they did, they used it to find the average energy per standing wave. They used the idea of classical physics, which is called theorem of equipartition equipartition of energy. Theorem of equipartition of energy or equipartition energy theorem. You must have gone through this theorem in your thermodynamics class. Now, how we state it? It is stated: at thermal equilibrium, Let me write it. At thermal equilibrium, there is associated an average energy of half kT per degree of freedom per molecule. Try to understand it. If you take an ideal gas, for example, I have some container. Now there is gas in it. Now if the gas is settled, that means some person is not stirring it, or some person is not compressing it or expanding it by some means. If the gas is allowed to settle, once it is settled, it will attain some temperature. Let T be its absolute temperature, that means temperature in Kelvin. Now, in this gas, which is at thermal equilibrium, it has attained an absolute temperature T. There is some energy, and that energy is shared between the molecules of this gas. Now, the theorem of equipartition of energy says that per molecule, per degree of freedom, half kT energy will be distributed. What is this K? You know it. It is Boltzmann constant. Boltzmann constant. Its value is small, 1.38 into 10 raised power minus 23 joule per Kelvin. 1.38 into 10 raised power minus 23 joule per Kelvin. What is the degree of freedom? A degree of freedom is a mode of energy possession. Mode of energy possession is called a degree of freedom. Now, you can, for example, possess energy in various ways, in various modes is the suitable word. Now, one mode of energy possession is one degree of freedom. Now, let us go to theorem. Theorem says when the gas is at thermal equilibrium at absolute temperature T per degree of freedom per molecule, there will be half kT. That means if uh, the molecule has 3 degrees of freedom, then its average energy will be 3 times half kT, because per degree of freedom it will possess half kT energy. Right? Now, this rule is called theorem of equipartition of energy. Now, this theorem of equipartition of energy is not just applicable to the container of gas molecules only. Right? I repeat, this theorem of equipartition of energy is not applicable only to the container of gas molecules. It is equally applicable to the container containing the radiation or mixture of radiation and molecules. So, in general, we say if there is a collection of entities at thermal equilibrium T, then per degree of freedom there will be half kT energy per entity associated. Right? Those entities can be molecules, those can be the standing waves in the cavity, or they can be mixture of radiation and matter, right? Now, this theorem of equipartition of energy was used by Rayleigh Jeans and Lord Rayleigh and James Jeans to find the average energy per standing wave in the cavity. So their idea was, in the cavity we have radiation, right? This radiation is at thermal equilibrium T, absolute temperature 3. Now I can use the theorem of equipartition of energy, but I have to first establish what is the number of degrees of freedom associated per standing wave. What they did for that? You might be knowing we define an oscillator called, let me change the color of my pen. We define an oscillator called harmonic oscillator. Is the model oscillator in case of oscillations. Now, if we have a one-dimensional harmonic oscillator, one-dimensional harmonic oscillator. Now, this one-dimensional harmonic oscillator has 2 degrees of freedom. Has 2 degrees of freedom. By that we mean it can possess energy in the form of kinetic energy, and it can possess energy in the form of potential energy. So it has 2 degrees of freedom. Now, idea of Lord Rayleigh and James Jeans was that the standing wave, each standing wave in the cavity, which is our black body, originates in an oscillating electric charge. Now, there are cavity walls. Radiation is bounded by cavity walls. So, idea is the radiation, the standing wave, it originates in an oscillating electric charge in the cavity walls. Or I should say it this way, when radiation is inside the cavity, the cavity walls, electric charge in the cavity walls are oscillating. Right? Why? Because radiation contains the oscillating electric field. That those electric fields act on the charged particles in the cavity walls. They make them oscillate. Now, when you know charging, if the charged particle is oscillating, it is an accelerating charge, and accelerating charge radiates energy back. Now, the oscillating charges in the cavity walls are oscillating in response to the presence of the radiation in the cavity. So, they are radiating radiation, they are absorbing radiation, is acting on them, but the system, that means the radiation which is emitted by these cavity walls, and the radiation which is in the cavity, inside the cavity, they all are in thermal equilibrium. That means the energy radiated by one oscillator on average in the cavity walls must be equal to the energy of a standing wave. I repeat, the average energy of the oscillator in the cavity walls must be equal to the average energy of an independent standing wave. Now, Lord Rayleigh and James Jeans considered the oscillator in the cavity wall as one-dimensional harmonic oscillator and said it has 2 degrees of freedom. Therefore, each oscillator must have energy 2 times half kT, which is kT. Now, since it is in equilibrium with the radiation, with the standing waves in the cavity, therefore average energy per standing wave must be kT. So this is the conclusion. So average energy per standing wave is, let me note it by epsilon bar, and let me make it some epsilon bar is 8. Let me name the equation second. So this is my average energy per standing wave in the cavity, and this is my number of independent standing waves per unit volume in the frequency interval nu to nu plus d nu. Now I am interested in u nu d nu. How I can get? I have simply multiplied it. Now u of nu d, which we call spectral energy density, which is the total energy per unit volume in the cavity in the frequency interval from nu to nu plus d nu. It is simply what? You have to multiply the average energy per standing wave with the number of standing waves per unit volume available in the cavity in this particular frequency interval. And you use equation first and second. That means you substitute for G nu d nu from first, and from second we substitute for average energy. So I will write here using equations first and second, we get this formula: 8 pi kt by c cube nu square d. Let me encircle it with some other color. This is my equation 3. 8 pi kt by c cube nu square du. Now this formula for spectral energy density is called Rayleigh Jean's law. We have obtained it. Now the question is whether this equation, if plotted with frequency at some particular temperature, can produce these curves or not. That we will discuss in the next lecture. Now I first summarize this result. So first you can see this, according to Rayleigh-Jean's law, this spectral energy density is proportional to temperature. C is constant, K is constant, C is speed of light, K is Boltzmann constant. It is proportional to nu square. That means as nu increases, this energy density is going to increase. You can see from the graph the error in this formula easily. In the graph, you can see first as nu increases, this spectral energy density increases, attains a maximum, then it goes down. Let me get this tool. I have this tool here. Where does this lay? No, not pen. So I will take this. Okay. So you can see first as frequency increases, spectral energy increases, then as nu increases, it decreases. But the equation is not indicating that. It simply says that as it is proportional to New scale, that means if you increase, it is only going to increase, not decreasing. That means there is an error in Rayleigh Jean's law. This Rayleigh Jean's law is not giving us the shape of the spectrum, right? Another thing which I must tell you, this average energy per standing wave is sometimes or always it is called classical average energy per standing wave, because the result which we use to obtain this, that is theorem of equipartition of energy, is fundamentally the idea of classical physics, right? So Rayleigh Jean's law is the classical physics attempt attempt made by Rayleigh and Jeans to use classical physics to establish or justify or explain the black body spectrum, which I indicated is not going to yield the shape of the curve. Right? Now, what is wrong and how to correct it, we will discuss that in the next lecture. Now, before leaving, I must summarize the lecture. First, we defined black body. Then we said it is an ideal body in case of thermal radiation. How we approximate in the lab, a hole leading into the cavity. Then we said when we experimentally see its spectrum, we get these types of curves. Now, to explain these curves in the 19th century, at the end of 19th century, there were two people, Lord Rayleigh and James Jeans, who attempted the solution of this problem. What they did, they considered the radiation in the cavity as a collection of three-dimensional standing waves. Then they obtained the formula for the number of independent standing waves in the cavity per unit volume in the frequency interval nu to nu plus d nu, then used the theorem of equipartition of energy to find the average energy per standing wave, which is kT, because they argued that the radiation is in equilibrium with the oscillators in the cavity walls. Oscillators are one-dimensional harmonic oscillators. They have 2 degrees of freedom. That means they must have 2 times half kT energy, which is kT. So standing wave must have the same energy where there is thermal equilibrium. Then they obtain this formula, right? Which appears to be false, which is false particularly at high frequencies. So we need to correct it. That we will discuss in the next lecture. Go through these lectures, make your notes, and prepare your exams. Don't waste your time, and don't forget to like, share, and subscribe my channel. Thank you. Assalamu alaikum.